White.
And Mr. Sadler.
And today we're going to talk about spring potential energy. Spring. That's a new word for us, but we've talked about another kind of potential energy, haven't we?
Yeah, gravitational.
And elastic, right? Elastic potential energy. So think back to the pole vault.
Right.
An experiment that we did.
Where I bend the pole and then it lifts me into the air.
Yeah. And so notice the equal sign. For some reason, the book changes its language, which I'm not a fan of. But spring potential energy and elastic potential energy are going to be the same concept.
So basically a spring or a bungee cord or a...
Right, so this is like a property of a material, or spring potential energy is due to a property of a material. And all objects, the word that I prefer over spring, of course, is elastic. And all objects have some elasticity, some ability to return to their original shape. And a spring is nice because unless you abuse the spring, it will hold its springiness. It will return to its original length. If you compress it or if you stretch it, that's due to this property of elastic. And so, for short, we'll probably call it SPE. And just like in Chapter 2, we'll say it's half kx squared. And once again, I imagine that some of you are still going to be calling this thing EPE. So my first question is, what is this cursive K representing?
It's just a constant.
Yeah.
And it relates to different materials or...
Right. So this number can vary. And I believe that you're going to see this maybe in a different investigation.
Yeah, I was thinking we do a thing with a piece of paper even where we...
Make a spring out of a piece of paper. So you're going to investigate this idea more than once in this chapter. But for the time being, spring constant, it's more of an engineering concept. It's measured in newtons per meter. So how much force is required to stretch it a certain length. And this is how much it stretches.
So some things don't stretch as much as others. Like a bungee cord stretches a lot, where a rubber pad doesn't stretch that much at all.
Right, and the stretching really has to do with how much can you push or pull on it before it breaks. And so once the material breaks, it's lost its elasticity. A 2x4 doesn't have a lot of elasticity. It has some. Not as much as, say, a pole vault or a pole for a pole vaulting event. A spring, it does a really nice job of returning to its shape, say, much better than a piece of paper.
Right.
Or even a rubber band. So this is just a concept. It's not a new concept, but we're going to be spending some time with this. And we're talking about this new kind of energy. And so one of my first questions is, does conservation of energy apply?
Of course.
Of course it does. Which would mean that the change in the energy is zero. So I like to write these first two lines because I think it's very telling. So at the beginning of any situation, like in the last podcast, we said, well, at the top it had gravitational energy and at the bottom it had kinetic. But realistically, when you're first doing these problems, you should say, well, what kind of does it have gravitational energy? Does it have kinetic energy? Does it have spring potential energy at the beginning? You should be asking yourself the same questions at the end.
The other thing that I like to ask is, if I'm trying to solve these problems, is where are those the max? Where are those zero?
Right.
So that I can convert from one to the other. So that's another question.
That's a nice thing to think about as well. Now, as we start plugging in for these things, remember in the last podcast, it sure was nice to cancel mass. That's not going to happen anymore.
Right.
If there's spring potential energy, you're going to have to deal with the mass in some way or another. So just be mindful of that. And what I really liked about the last podcast is we got that FET out and we looked at the energy skate park.
And we could see the graph as it moved from one energy to the other energy.
Right. So we found another FET, And we decided to look at that. And as we look at that FET there, all right, we've got it in slow motion. So this is 1/16 the actual time. We see that the total energy remains constant, which means energy is being conserved. We see at the top it has lots of gravitational potential energy. When it's moving, it has its kinetic energy increases. As it slows down, that value drops.
And at the bottom, it must have.
And at the bottom, when the spring is stretched, it has a lot of elastic potential energy. And we can go through this cycle over and over again.
But the important thing to notice is that the total remains the same. It just switches from one to the other. The other thing is you probably want to look at where are these things the max? Where should I be looking for the max?
Right.
What can I
So-
compare?
Right there. We're at the top. It's got the maximum amount of gravitational potential energy. The spring is not being stretched at all, so that's a 0. And it's not moving, so the kinetic energy is a 0. When we go back to 1/16 of our time, when is kinetic energy a max? About right there. And when kinetic energy is at a maximum value, okay, it's done speeding up. It's at a point where it's about to start slowing down. But you'll notice, while this is a maximum, we still have a lot of gravitational energy, and we're giving the spring some elastic energy at that point. We play it back, right there.
Now we have no gravitational.
Well, no, we have no kinetic because it stopped again.
Right.
It's still above the ground. I'm not sure where the FET thinks 0 is.
Right.
Now, I suppose
Just
we
like
could.
the skate park, it wasn't exactly
Yeah.
0, right?
And so, but this one we can't adjust it though. But you'll notice it's got a maximum amount of elastic or spring potential energy. And when we play it again, we can view these points over and over. Now, if you tried to watch this in real time, it's really hard to check that out. The only thing you can really see is the
So total remains
energy
the same.
stays the same. And you can do all sorts of things here. You can change your location. You can make zero gravity environment. You can adjust the friction of the spring. This is a really nice tool. Well, what I like about it is that we can slow it down, see it in slow motion. So those graphs are on page 375 of your book. If we wanted just to look at a sample problem, maybe just conceptually to look at it on page 377, it says a spring pop-up toy with a mass of 0.02 kilograms reaches a maximum height of 0.5 meters. The compression length of the spring is 0.03. Find the GPE at the top, the spring potential before the pop, the spring constant K, and the kinetic energy at the moment the spring toy leaves the ground. So this toy is different than the FET we just saw. That was a mass hanging from a spring and it oscillated. This is a little bit different.
It's like a popper toy, so it has elastic potential energy sitting on the ground just before it pops.
Right. So if I were to try and draw a picture of this, which I do recommend, so here's my toy. It's all bound up. It's on a spring. Okay. So at the bottom here, the spring is all smashed together. It's got no height, and so what I would do is I would pick the bottom of my spring to be height, and so it's a 0.
Right,
It's got a lot of spring potential energy right here.
right.
Okay, the moment it leaves the ground, okay, it's got a maximum amount of kinetic energy. It has a maximum amount of spring energy there.
Right.
At some point here, before it gets to the top, okay, it's got no spring, but it's got some KE, and it's got some GPE.
Right.
At the top,
It's got a maximum
it's got a maximum,
GPE.
yeah. And so that means that the speed is 0.
Right.
And then it comes all the way. So this was the progression. This was step 1, 2, 3, 4. Well, then we would just say, well, this is also step 5, step 6.
Right.
And
Back down.
back, if the spring were to compress back down, then that would be step 7. And so you can work your way through this. It tells us how high it goes. It tells us in the problem that it reaches a height of 0.5 meters.
So that's going to make it very easy to calculate gravitational potential energy.
Yeah. And so if we know GPE max, assuming that there's no other outside friction, then we know the total energy at all these different points. And so that since they tell me M, and I know G and H was just provided, then the gravitational potential energy at the top is about 0.098 joules. Not a very nice number to deal with, but it works nonetheless. It wants to know the spring energy before the pop. Well, according to energy conservation,
Right, has to be
then
the same.
it has to be the same. So spring potential energy max would just be 0.098. And if they wanted to know the spring constant, I just set my spring energy equation to it.
Right.
They tell me that the spring compresses some 0.03 meters, so it's just a matter of solving for K. And so I determined that K is equal to 2 times this tiny obnoxious number divided by x squared. And when I do that, I get about 218 newtons of force per meter. And then the last thing is it wants to know the kinetic energy as soon as it leaves the ground. And so,
I know that the kinetic energy is going to be exactly the same again,
right, because of energy
but
conservation.
even beyond this, I could calculate the speed at
Yeah.
the speed as soon as it leaves the ground, the maximum kinetic energy. I could do that too. So it doesn't ask that, but you could figure out how fast it's going.
Right.
So that just goes to show you that you can go even above and beyond this.
So, KE max would be the same as GPE max is the same as spring potential energy max.
Correct.
You could take that 0.098 number and set that equal and then rearrange things. I wouldn't do that. I would do this. And I'd
Right.
cancel mass.
Right.
And we saw this solution last time. I love that solution because it just keeps showing up in
Well,
physics.
and I could do so many other things with this too.
Right, you could figure out the momentum at that moment. You could figure out that's what it is. We'll use the different springs. We talk about spring force and
Right.
Hooke's law. We can figure out the spring force required, and to do these things as
It's a
well.
projectile. I could figure out the time that it's in the air.
Yeah.
Could do all kinds of things.
So what we're trying to say, and what I've been preaching, at least in my class, is that all the stuff we've learned this semester is showing up in Chapter 4.
Right.
We're not actually learning anything new. We're just applying it in a different way.
Correct.
So I believe that wraps things up for spring potential energy. And we visited energy conservation one more time. So signing off, this is Mr. White.
And Mr. Sadler.